Welcome to Bethlahem Institute of Engineering. Bethlahem Institute of Engineering is affiliated to Anna University, Chennai and approved by AICTE, New Delhi. This institution was established in the year 2008.
Good morning. Welcome to Digital Electronics class. Before entering into our course Digital Electronics, let me give an introduction to Digital Electronics. You are familiar with the term electronics. What is electronics? Electronics is the branch of science which deals with the study of flow and control of electrons and also on the behavior and effects of electrons in vacuums, gases and semiconductors. In simple terms, electronics deals with flow and control of electrons in vacuums, gases and semiconductors. We live in an age of information technology, and electronics is the foundation of this information technology. Electronics is not only the foundation of information and technology, it also forms the basis of computer. So the electronics is further divided into analog electronics and digital electronics. That is, electronics is broadly classified into analog electronics and digital electronics. So here we shall discuss the difference between analog signal and digital signal. What is analog signal? Analog signal take on any value across a continuous range of voltages, and digital signal takes only two discrete values of voltages. This is an example for analog signal and this is an example for digital signal. Analog, it represents continuous range of signals. That is, analog signal can carry any values across this continuous range of signal. That is, it can take 1, 1.2, 100, 105, 0.2, 3, 4, anything. Any value. It can take any value across the continuous range of signals, voltages. But digital signal can take only two discrete values of voltages. So that is 0. This low level represents 0 and high level represent 1. So digital signals can take only two levels or two values, 0 and 1. So this is an example for digital signal and this is an example for analog signal. And this clock with hands, that is with minute, hand, second hand and hour hand, is an example for analog device, and this clock with digital display is an example for digital device. So analog signal can take on any value across a continuous range of signal, but digital can take only two discrete values, that is 0 and 1. So analog can be of any values, 1, 1.2, anything across any continuous range of values, but digital signal can take only two values, 0 and 1. What is digital electronics? Digital electronics represent information with only two discrete values, 0 and 1. Digital electronics represents information with only two discrete values, 0 and 1. So discrete means distinct or separated. It is opposite to that of analog. Analog means continuous, but discrete means separated or distinct. In ideal cases, no voltage, for example 0 voltage, represent this 0 value, and full source voltage, for example 5 volt, represent 1. But in practical cases, low voltage, that is less than 1 volt, represent 0, and high voltage, that is greater than 4 volt, represent a 1. So in simply, so no voltage means it is represented as 0. No voltage or low voltage. Then full source voltage or high voltage means 1. Digital electronics consists of only two discrete values, 0 and 1. Discrete means distinct or separated, and no voltage is represents a 0, and full voltage or high voltage represent 1. So why we move for digital electronics? As we have discussed in the previous slides, electronics is categorized into analog electronics and digital electronics. So, but we prefer digital electronics. Why? What's the reason? So there are a lot of advantages of digital signal over analog signal. That's why we prefer digital nowadays. So what are the benefits of this digital signal over analog signal? They can be processed and transmitted efficiently, and the digital signals can be reproduced with greater accuracy, and they are less affected by noise. And well, data protection is done in digital signals, and they are programmable, and the cost is less compared to analog signal, and the speed of digital signal is high compared to analog signal, as well as the storage capacity of the analog signal is high when compared to storage capacity of digital signal is high compared to analog signal, and the design process is also easy in digital when compared to analog. Because of all these advantages, digital signals are preferred over analog signals. Okay. So that's why in almost all areas of our life, digital electronics or digital devices are used. And this digital system started back in 1940s, and these are the areas that are covered by digital systems: still pictures, video, audio, telephone, traffic lights, animation, communication, business transactions, spacecraft guidance, medical treatment, weather monitoring, internet. So almost all areas are covered by the digital systems. That's why digital electronics is preferred over analog. Coming to the digital circuits, the digital circuits can be categorized into two types: combinational circuits and sequential circuits. The sequential circuits are further divided into synchronous sequential circuit and asynchronous sequential circuit. Digital circuits are broadly classified into combinational circuit and sequential circuit. Then sequential circuits are further classified into synchronous and asynchronous sequential circuits. So in the syllabus of the course Digital Electronics, most part is covered by this digital circuits. That is, the second unit deals with combinational circuit design, and then third and fourth explain about synchronous sequential circuit and asynchronous sequential circuit. And the first unit is all about the digital fundamentals. So this is the syllabus of the course Digital Electronics. First unit is about digital fundamentals, and the second unit is about combinational circuit design. Third unit is synchronous sequential circuit, fourth asynchronous sequential circuit, and the last unit deals with memory devices and digital circuits. So second, third and fourth unit describes about the types of digital circuits. First unit is about fundamentals, second, third and fourth unit describes about the digital circuits, and fifth unit is about the memory devices and digital integrated circuit. So this is the brief introduction of digital electronics as well as the syllabus. Now let us pass on to unit 1, digital fundamentals. First unit, digital fundamentals, covers number systems, complements, codes, Boolean theorems, logic gates, sum of products and product of sums, Karnaugh map minimization, and finally Quine-McCluskey method of minimization. So in this class we will be discussing about this number systems. What is number system? So it is a code using symbols that refer to a number of items. For example, the decimal number 5 is represented by the symbols 1, 0 and 1 in binary number system. So what are the symbols here? In binary number system, this 1, 0 are the symbols. And in decimal, we have 10 symbols. This 5 is also a symbol. So can you understand what is symbol? So symbols means the elements present in a particular number system. In binary, we have two symbols, 1 and 0. And this number 5 is represented as 101. That is, this 101 is the code which uses the symbols 1 and 0. Okay. So that's the meaning of code using symbols. So here in our syllabus we have 4 number systems. First is binary number system, decimal, octal and hexadecimal number system. First, decimal number system. Decimal number systems uses 10 symbols. So the 10 symbols are 0, 1, 2, 3, 4, 5, 6, 7, 8 and 9. Since it has 10 symbols, the base of the decimal number system is base 10 or radix 10 system. Decimal number system uses 10 symbols. The symbols are 0, 1, 2, 3 up to 9. Since it uses 10 symbols, it is known as base 10 or radix 10 system. Binary number system uses only 2 symbols, 0 and 1. Hence it is known as base 2 or radix 2 system. So can you understand what is base? So base is based on the symbols present in a particular number system. So in binary number system, only 2 symbols are there, 0 and 1. Hence it is known as base 2 or radix 2 system. And in decimal number system, we have 10 symbols, 0 to 9. Hence it is known as base 10 or radix 10 system. So next is octal number system. So octal number system uses 8 symbols, 0 to 7. Hence it is known as base 8 or radix 8 system. So octal number system uses 8 symbols, 0 to 7. Hence it uses 8 symbols. It is known as base 8 or radix 8 system. So next is hexadecimal number system. It uses 16 symbols, that is 0 to 9 and A to F. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then A, B, C, D, E, F. Totally 16 symbols are there. Hence this hexadecimal number system is known as base 16 or radix 16 system. So in hexadecimal number system, both numbers and alphabets are present. And totally 16 symbols are there. Hence it is known as base 16 system. So now you can understand what is symbols. Symbols represent the elements present in a particular number system, and base represent the number of elements or symbols present. So we have seen 4 number system: decimal, binary, octal and hexadecimal. So decimal means it has 10 elements. So the base is base 10. And binary, only 2 symbols or elements, 0 and 1, so the base is 2. Octal, it consists of 8 symbols, 0 to 7, hence the base is 8. Hexadecimal number, it uses 16 symbols, 0 to 9 and A to F, hence the base is 16. And this chart shows the relationship between decimal, binary, octal and hexadecimal. So for the first 16 numbers, 0 to 15 decimal numbers, the relationship between binary, octal and hexadecimal numbers are given. For example, see here, the decimal number and hexadecimal number 0 to 9 and 0 to 9. Up to 0 to 9, both the decimal and hexadecimal is same. But from 10, in decimal after 9 you have 10, but in hexadecimal after 9 you have A. Then after that it goes on like this, B, C, D, F. Here we know that in our decimal system we use 10, 11, 12, 13, 14, 15. Similarly in octal, you have up to 7, 0 to 7. After 7 you don't have 8 because there is no symbol like 8 in octal. So after 7 it uses 10, 11, 12, 13, 14, 15, 16 up to 17. Okay. Have to memorize this table, relationship table, which will help you to solve the problems. The number-based conversions. So number-based conversions means how to convert a number from one number system to other number system. So for example, in question, decimal number will be given and you will be asked to convert to other number system such as binary, octal or hexadecimal. So we will learn about these things. Number based conversion, that is conversion of one decimal number to other decimal number in this portion, in this class. So first is we are going to discuss about the conversion of decimal numbers to other base numbers, that is how to convert a decimal number to binary, octal and hexadecimal numbers. So before discussing about the conversion, so we should know what is integer part and fractional part of a number. So for example, consider a number 4567.234. So here this part 4567, which is present before this decimal point, is known as the integer part, and this part 234 is known as the fractional part, and this point is known as the radix point or integer point. Sorry, clear what is integer part or fractional part? So integer part or fractional part of a number means the number that is present before this part. Integer part represents the number before the radix point or decimal point, and fractional part represents the number after this decimal point or radix point. And so this is the procedure for conversion of integer part of a decimal number to other number system. So as we have seen, a number can consist of integer part and fractional part. The procedure to convert the integer part and fractional part of a decimal number to other number system is different. And here this shows the conversion of integer part of a decimal number to other number system. So while converting the integer part of the decimal number to other number system, the first step is have to divide the decimal number by base of the number system to which it is to be converted, and you have to store the remainders in array. So first you have to divide the given number by the base of the number to which it is to be converted, and you have to store the remainders in array. Then you have to divide the quotient, that is you have to continue the division till we can't further divide. You have to continue this division process till we cannot further divide. Then you have to write the equivalent binary number. That is, main thing you have to understand while converting the integer part of a number to decimal number, other number, we have to follow division method. And for division, we have to use the base of the number to which it is to be converted. So we'll be clear with this procedure while solving the numericals. Then this is the procedure for conversion of fractional part of the decimal number to other number system. So here we are following a multiplication procedure. We have to multiply the fractional part of a decimal number by the base of the other number. And you have to continue the process till we get the fractional part as 0. So we will get the clear idea of this conversion while solving the numerals. So the first example, it is convert decimal number 41 to binary. So here the given number is decimal number. First you have to identify from the question the given number is in which number system. Here it is given decimal number system. Then you have to check to which system it is to be converted. So here we are asked to convert to binary. Then we have to see what part is given, whether integer part is given or fractional part is given or both the parts are there. So in this question, only the integer part is given, 41 that represent the integer part. So if integer part is given, you have to follow the first procedure, that is the division procedure. First you have to write the number 41. Then you have to divide by 2. Why we are using 2 as the divisor? Because we are asked to convert to binary. The base of the binary is 2. That's why we are using this 2 to divide 41. Then again you have to divide this. While dividing 41 by 2, you will get the quotient as 20 and remainder as 1. Further dividing, you will get the quotient is 10 and remainder is 0. Again you will get 5 as quotient and 0 as the remainder. Then 2 as the quotient and 1 as the remainder. And finally you will get 1 as the quotient and 0 as the remainder. And here further we can't divide this 1 by 2, so we have to stop with this. Then you have to write the answer from bottom to top. It's 1 0 1 0 0 1. So in this way you have to write the answer. So keep it in mind, you have to write the answer starting from the bottom and moving towards the top. And while writing the answer, the given number system, you have to represent it. It is 41. It is in which number system? Decimal. So you have to give the basis 10. And now we have converted into a binary number system. The base of the binary is 2. So I am repeating the procedure. First you have to check the number system. The given number is in which number system? Here the given number is in decimal number system. Then you have to look for the number system to which it is to be converted. Here it is binary. Then we have to check for the given number, that is whether the integer part is given or fractional or both is given. And here the integer part is given, that is 41. It is the integer part. So the procedure to convert the integer part to binary number is, or integer part to any other number system, is division method. So you have to first write the given number and you are dividing by 2. Why we are dividing by 2? We are asked to convert to binary. The base of the binary is 2, so we are dividing by 2. We have to divide and write the remainder like this and quotient as like this. And you have to continue the division till you can't further divide it. Then you have to write the answer from bottom to top like this. So this is the way to convert decimal number to binary. The same procedure we have to follow for converting any decimal number to other number system also. Only the divisor varies. We will look on to the next example. Example 2, convert decimal number 153 to octal. So here also first we have to check which it is in which number system. Your number is in decimal number system and we are asked to convert to octal. Then here which part is given? Integer part is given. So if integer part is given, we have to follow the division method. So 153 have to divide by 8. because you are asked to convert to octal number. The base of the octal is 8. So you have to divide by 8. So while dividing 8 by 153, the quotient is 19 and the remainder is 1. So further dividing 19 by 8, you will get the quotient as 2 and the remainder is 3. Then you can't divide, so we can stop with this and you have to write the answer from bottom to top. That is 2, 3, 1. And you have to represent the base also. The given number is in base 10. And you are asked to convert to octal. So the answer is in base 8. So this is the procedure to convert a decimal number to octal number. Here only the integer part is given. So integer part means we have to follow the division method. For dividing, the divisor is obtained from the question. So here the question, it is asked to convert to octal. So we have used 8. 8 is the base or radix of the octal number system. So we have used 8 for division. And then we have to write the answer from bottom to top. So next is convert decimal number to hexadecimal number. So here also the given number is in decimal number. Then you are asked to convert to hexadecimal. Only the integer part is given. Again you have to follow the same division method. But what's the divisor here? It is 16. Why? Because for hexadecimal number, the base is 16. So we have used 16 as the divisor. Then for the dividing, so while dividing 650 by 16, you will get the quotient as 40 and remainder as 10. And for the dividing, you will get the quotient as 2 and the remainder as the 8. And in hexadecimal number, you have to keep one thing in mind. If a number is like this 2-digit number, you have to write the corresponding hexadecimal number. So already in the hexadecimal chart, I have shown you the corresponding hexadecimal number of a decimal number 10 is A. So you have to write A in the place of 10 because we have performed a division for a decimal number. So 10 is a decimal number and you have to write the corresponding hexadecimal number of decimal 10. For decimal number 10, hexadecimal number is A. Till 9, decimal number and hexadecimal are same. 0 to 9, both the decimal and hexadecimal are same. But after 9 in decimal we have 10. In case of hexadecimal, after 9 you have A, B, C, D, E, F. Okay. So we are replacing the 10 by A. So the answer is 2, 8, A. Writing the answer, 650 is in hexadecimal, so I have to give the base as 10. Then 280, it is in 60. Till now we have seen 3 examples. Now the 3 examples, the given number is decimal number and you are asked to convert to some other system. And only the integer part of this number is given, so you have used decimal, that is division method. Next is convert 0.6875 to the base 10 to the binary. So here as in the previous case, the question is not, in the question it is not given as decimal number. The previous 3 examples, the question it is mentioned decimal number. But here it is not mentioned decimal number, but we have to identify the given number. So here the base is given as 10. So from this we can identify the given number is decimal number. So if the number system is not mentioned in the question, from the base of the number you have to identify to which number system it belongs. So here then this number 0.6875 belongs to hexadecimal number and you are asked to convert to binary. And this part represents the fractional part of the number. For fractional part, the procedure is like this. That is, we are following some multiplication procedure. First, you have to write the given fractional number. Then you have to multiply by 2. Why you are using 2 as the multiplier? because we are asked to convert to binary, we have written 2 as the multiplier. So after multiplying, we will get the product as 1.3750. Here this one is the integer and this 0.3750 is the fractional part. We know that. Here we have to write this integer behind the number like this. And we have to write or copy this 3750 to the next step. There is a fractional part to the next step. We have to write the integer behind that number like this. And we have to write the fractional part to the next step. That is, we have to copy the fractional part to the next step. And you have to multiply by 2. So while multiplying by 2, we will get the product as 0.750. Here the integer is 0. We have to write this 0 behind it. And 7500 is the fractional part. You have to write the fractional part in the next step. Again, you have to multiply by 2. The product is 1.500. 1 is the integer part. We have to write the integer part behind this. And this fractional part is written in the next step. And again, multiply by 2. You will get the answer as 1.0000. And 1 is the integer. And the fractional part is 0. So if we get the fractional part as 0, we can stop with this. If the fractional part is 0, we can stop the process with this. Otherwise, we have to continue till we get the fractional part as 0. So it can't stop if we get the integer as 0. See, in the second step itself, we got the integer as 0, but we didn't stop. We have to stop the procedure when the fractional part is 0. See here, we got the fractional part is 0, so we have stopped with this. And then you have to write the answer from top to bottom like this. First you have to write this 1, then 0, then 1, 1. 1, 0, 1, 1. Before that you have to place a decimal point. Because we are dealing with this integer part, we have to put a decimal point here. So can you understand? Here we are asked to convert a decimal number fractional part to binary. So first you have to write the fractional part of the given decimal number. Then you have to multiply by 2, since the base of the binary number which we are asked to convert is 2. We are multiplying by 2. Then you have to write the product. We will get a product. And in that you have to write the part behind it and the fractional part the next step. And again you have to multiply by 2 and you have to continue the process till you get 0 in the fractional part. If you won't get 0 till 8 or 9 stop in the fractional part, we can stop with the 8 or 9 the iterations. Then you have to write the answer from top to bottom and we'll get like this. Convert 0.513 to the base 10 to octal. Here also the question it is given base 10. So it is a decimal number and the number we have only the fractional part and we are asked to convert to octal. So for fractional part we have to follow this procedure. Since we are asked to convert to octal, we have to use 8, that is the base of the octal number, to multiply the given decimal number. Here the given decimal number is 0.513. So we have to multiply the 0.513 by 8. 8, it is the base of the octal number. So we have to multiply by the base of the number system to which it is to be converted. Then again you will get a product. This integer part you have to write here. This fractional part you have to copy down to the next step. Again you have to multiply by 8. You will get a product. So I have to write this integer part here, this fractional part to the next step. Have to continue till you get 0 in the fractional part. But in this problem, we won't get 0 till this 8th iteration. So we have stopped with this. So general procedure is have to proceed till we get 0 in the fractional part. But if you won't get 0 till 8th or 9th steps, you can stop with this. And you have to write the answer from top to bottom like this: 40651764. So before that you have to place a point. Don't forget to place a point. And then you have to write the answer like this. Given number in base 10 and the answer we got in base 8. So are you clear with this? So next problem. We are asked to convert 22.64 to the base 10 to hexadecimal. So here also the given number is in base 10, so it is in decimal form. And here we have both the integer and fractional part. So you have to follow the procedures for both integer as well as fractional part. So first consider the integer part. 22 is the integer part. For integer part we know which method you have to follow, that is division method. And we are asked to convert to hexadecimal, so I have to divide by 16. So while dividing this integer part, that is 22 by 16, the quotient is 1 and the remainder is 16. So we can't further divide this 1 by 16, so we can stop with this. Then you have to write the answer. 22 to the base 10 is equal to this 16, 1 to the base 16. Coming to the fractional part, that is 0.64. For fractional part, we have to follow this multiplication procedure. Since we are asked to convert to hexadecimal, we have to multiply the fractional part by 16. So while multiplying 0.64 by 16, we'll get the answer as 10.24. Have to write this. This is 10 is the integer part, so we have to write the 10 here. This 10 is in decimal form, so you have to write the corresponding hexadecimal form, that is A. Then you have to copy down 4 to the next step and multiply by 16. The product is 3.84. 3, the integer, I have to write behind this, and 0.84 you have to copy to the next step, and you have to follow the same procedure. Here you will get 13 as the integer. So 13 is in decimal form. You have to write the corresponding hexadecimal, that is 8. And you have to continue till the fractional part becomes 0. If you don't get the fractional part as 0, till 8th or 9th step, we can stop. So we have stopped here and we have written the answer. This A first. A, then 3 is 3, then D, 7, 0. That is from top to bottom, you have to write the answer. Now finally, you have to combine both the answer and write. So for 22, the number we got in hexadecimal is 16. And then for the fractional part, we got the answer as A3, D7. So we have a 0, A also. So this is the way in which we have to convert any number from decimal to other number system. So summarizing the conversion part. So we have seen about the conversion of decimal number to other number system. So there we have two parts in a number. There can be integer part and fractional part. If you are having a integer part, we have to follow the division method like this, and the divisor here will be the base of the number system to which it is to be converted. And for fractional part, you have to follow the procedure like this. And here one more thing, while converting to integer part, converting the integer part, you have to write the answer from bottom to top in this order. And in the fractional part, you have to follow from top to bottom. So we clear with this? So this is the conversion of any decimal number to other hexadecimal number system. So main thing, for integer part you have to follow the division rule, and for division you have to use the divisor as the base of the number system to which it is to be converted, and you have to write the answer from bottom to top. And for fractional part, you have to follow this multiplication process, and then you have to write the answer from top to down. And the multiplier, it is based on the question we are given. That is the base of the number system to which it is to be converted. So now let us recall what we have discussed in this class. So first we have seen what is electronics, type of electronics, analog and digital electronics. Then we have compared analog signal with digital signal. Then we have seen the advantages of digital signal over analog signal and the areas that are covered by digital signal. So digital signal covers almost all areas of our life. Then we have seen about digital circuits. Digital circuits are widely classified into two types: combinational circuits and sequential circuits. Sequential circuits are further divided into two types: synchronous and asynchronous. And the first part of our syllabus gives the digital fundamentals, and second, third and fourth unit describes about the digital circuits, and fifth unit is memory devices. Then we have seen about then we have started the first unit. There we have seen about number system. For number system we have discussed binary, decimal, octal and hexadecimal. Then we have seen number base conversion, that is conversion of decimal number to other base systems. Thank you.